Welcome back. Hope you had a good lunch. Got more of the same, except not exactly the same. This third session is on shear walls, and it is a different set of problems from frames. And as I think I said before, it's substantially more difficult. So the topics for this session, I'm going to look at the main aspects of behavior for two-dimensional walls to begin with, and then modeling of 2D elastic walls, modeling of 2D inelastic walls for bending and then for shear, then move on and look at three-dimensional walls, then move on to the demand capacity calculation, first for the axial bending deformation, which will usually be inelastic, then for shear strength and shear deformation, and finally a number of other aspects, including p-delta effects, out-of-plane behavior, and a few other things. And we're talking about in-plane behavior, since this is 2D, and so we'll talk about out-of-plane behavior later. And we have piers, coupling beams, maybe some deep coupling panels, and a few other things. And as indicated here, that this is, I think, a reasonable interpretation of the behavior is the first one here. Even though this is a pretty fat pier, they act pretty much like columns, and plane sections remain essentially plane. Now, that doesn't mean to say they're necessarily governed by bending. They may be governed by bending, or they may be governed by shear. The key thing is that it's really not unreasonable to assume plane sections remain plane. I'm going to say more about this later on, because you might look at this and say, wow, that can't be right. Coupling beams may be slender or they may be deep. Slender coupling beams may be governed by bending, or they may be governed by shear. Probably more likely be covered by shear, be controlled by shear than by bending. Deep coupling panels are almost certainly governed by shear. Other issues, the foundation may have significant flexibility and not be rigid. And it is worthwhile pointing out that the panel zone areas in here tend not to be very highly stressed. Thank you, Syed. It's the piers and the beams. I'll use the term piers and beams, even though they may be deep coupling panels. This is looking now at pier behavior. And on the left, we have a pretty slender pier and with fairly substantial coupling beams. And for this case, the bending moment diagram for that pier might be pretty much what it might be for a column in a frame. Notice there is a difference here where the moment varies over the depth of the beam. It's not necessarily a straight line, but let's not get hung up on details. When we look at the wide pier, this is not going to be affected as much by the coupling panel, so the shape of the moment diagram is more likely to be like that for a cantilever. And then, theoretically, at least if you do a linear elastic analysis, the shear stresses could vary substantially over the width of the pier, but you don't worry about that for design. You look at the complete width, and you design based on an average shear stress, and so that is what you would do. So the fact that the shear varies over the width of the pier probably doesn't matter that much. And I'll have more to say about that later also. Let's look at coupling beam behavior, firstly in bending, and we'll do shear in a moment. And two diagrams here, one elastic and one actual. According to elastic behavior, the curvature will vary linearly along the length. The deformations may be substantially shear deformations, which would be constant over the length, and some bending, and it depends on the proportions of the beam, which is dominant, bending, deformation, or shear. But the curvature will vary linearly. And one thing that may happen, I haven't shown this here, but there may be substantial local deformations where the beam meets the pier. This is what you would get from an elastic analysis. The actual behavior is likely to be substantially different. Again, we're talking here bending, we'll do shear in a moment. A crack may open at the face of the wall because of your bond slip within the wall or within the beam. And if it's controlled by bending, a plastic zone may form near the end. This is substantially different behavior from what you would get from a linear analysis. If you look at shear, elastic behavior, a beam with conventional reinforcement and a beam with diagonal reinforcement. In the elastic behavior, you have a tension diagonal and a compression diagonal, and elastic analysis would say that the amount of stretching of the tension diagonal is the same as the amount of compression of the compression diagonal. It's basically pure shear behavior, and there's no extension of the beam as a whole. It just deforms in shear. And there may be an added bending deformation, but this is just shear. If you look at an actual behavior with conventional reinforcement, I think you can sort of reasonably argue we'll form diagonal cracks, but the majority of the deformation will be yield of the shear reinforcement. The horizontal steel may not yield, and the beam as a whole doesn't extend very much. When you come to the diagonal reinforcement, however, you have a tension diagonal, and the perspective here is a little strange, a tension diagonal and a compression diagonal. The compression diagonal has got concrete, and it's pretty strong, and it doesn't deform very much. The tension diagonal is the one which yields because it's just the steel and the concrete cracks. So you'll get a smaller deformation in the compression diagonal than you will in the tension diagonal. And what this means geometrically is that the beam has to extend in order for it to work in this manner. If it didn't extend at all, the deformations of the two diagonals would have to be the same. If the deformation of the tension diagonal is to be larger than that of the compression diagonal, which is usually required for this to work properly, it must extend. And of course, later on, we're talking what happens if it can't extend because it's confined in some way. If you look at squat or irregular walls, it could be something like this. And I'm not going to spend very much time on this because they tend to be a lot more complex. Piers and beams, I think, are more likely to be non-slender, and they're more likely to be controlled by shear. Some parts like this, it's not obviously a beam, and it's not obviously a pier. In a situation like this, where a lateral load is shown, it's possible for a tension tie to develop through here at the sufficient vertical reinforcement, coupled with a compression diagonal, and you can develop strut and tie or truss behavior, which can dramatically strengthen the beam. And shear can be more of an issue. It's possible to get not conventional shear involving yield of the shear reinforcement and things like that. It's just sliding shear along a construction joint or along the base of the structure. And these things can be rather difficult to model. So those are the main aspects of behavior for 2D walls. What about modeling 2D walls? And we're talking here about elastic walls, so we'll talk about inelastic walls in a moment. Firstly, a frame model or a wall model, and these two diagrams show a frame model on the left with columns and beams and rather substantial end zones for the beams. And a simple wall could be modeled like this. Or you could use 4-node or even higher order finite elements. This is not necessarily a good mesh. It just indicates a type of mesh that might be used. But this would now be using solid type elements. And I would argue that a model with wall elements is usually better. And in this seminar, I'm not going to consider frame models. Or they could be used. If they were, you would use the principles we discussed in the last session. Perform has a wall element, and we're looking here only at the in-plane behavior. And basically, this is what it does. It's got, in the vertical direction, it's got an extensional mode of deformation and a bending mode. In the horizontal direction, the same, a horizontal extensional mode and a bending mode. It's got a single shear mode, and it's got 3 rigid body modes: vertical, horizontal, and rotation. So those of your finite element theoreticians recognize it's a 4-node finite element with 2 displacements per node, or a total of 8 degrees of freedom, and these are the deformation modes. Notice that the axial strain is constant, the curvature is constant, and the shear strain is constant. These are all constant deformation elements, so rather low-order elements. The elements are shown here as rectangular. They don't have to be rectangular, but it's a good idea to keep them roughly rectangular. Let's have a look at what it means to use these wall elements, and remember it's still elastic, to model bending behavior. And I'm showing here a horizontal beam. It could also be turned through 90 degrees and be a pier. And the left is the exact elastic solution. The shear force is going to be constant, and the shearing deformation will also be constant. The bending moment will be linear, and the curvature will also be linear. The finite element model, again, the shear force will be constant, and the deformations also. But there's a difference when you get to bending. The bending moment will still vary linearly, but because these are constant curvature elements, the curvature is constant over the width of the element, and it's based, it's the curvature at the center of the element which is used to determine its behavior. So this is an approximation to this. The thing to look at next is what's the level of the approximation. And let's take a beam, and let's look at beams with different span to depth ratios and different meshes, and have a look and see what happens. Let's do an elastic beam with a rectangular section. The shear modulus typically 0.4 times the Young's modulus. And let's here, to be simple, assume the shear area is equal to the actual area. Maybe it should be 5/6 of the actual area, but let's not quibble about minor issues like that. And let's look at the ratio of the finite element deflection to the exact deflection for different depth to span ratios and different numbers of elements. The first column here is a depth to span ratio of 1, 1.5, or a span to depth ratio of 2, and a span to depth ratio of 4. First row, a single element, 2 elements, 4 elements. And we're looking here basically at how accurate would the displacement be calculated using these elements. Well, for a 1-to-1 span to depth ratio, it doesn't really matter whether you use 1, 2, or 4 elements. It's pretty much exact. If you have a 2-to-1 span to depth ratio, this might regard this as not being accurate enough, but certainly 2 elements is sufficient and 3 elements is definitely ample. If you look at what is going to be a pretty slender beam for coupling beams, a single element would not be accurate enough in terms of displacement. This might be, although it's a little questionable, but even here, 4 elements is ample for picking up the elastic stiffness. So just give you an idea of how, even though the element has got constant curvature, how accurately can it capture the elastic stiffness. So based on this, what might be a reasonable mesh if you're doing an elastic analysis? And here's what I'd say, is if you have a slender beam, I would suggest using a beam element. If you have a deeper beam, then you might consider using wall elements and 2 or possibly 4 elements along the length. For a slender pier, wall elements and 2 to 4 elements along the length. For the wide pier, which is basically a vertical cantilever, you really have got 1, 2, 3, 4, 5 elements over the length. If you only use 1 element over each of these stories, basically. So a single element over the story height, I think, should be okay. There's no reason to use more than that. Across the width, I've argued that plane sections remain essentially plane, so a single element over the shear width should be okay. You might think, gee, I really should have several elements over the width. I don't think so. 1's enough. If it's reasonable to assume plane sections remain plane, and I think it is, 1 element should be enough. If in doubt, you might use 2 or 3 elements. I'd be inclined not to. Let's look at the model for a slender coupling beam. And now I'm talking about perform, because perform does have certain restrictions on the way you model these. This is what we're talking about, a couple of wall segments with a fairly slender beam. You would model this with a beam element. I'll talk about the details in a moment. But you must, in order to connect this beam into the wall element, you must have some embedded beams alongside it. Otherwise, it basically is a pin connection between the beam and the wall elements. And that's just one particular detail. The coupling beam can have plastic hinges for bending and or shear. It depends whether it's controlled by shear or bending, and that's your decision. The embedded elements shouldn't add any stiffness to the wall. And there is, in the seminar notes, is a brief paper which discusses the modeling of coupling beams and gets into this issue of what properties you might assume for the embedded beams. If you have a deeper coupling beam, which is shown here. You can either use wall elements or you can use beam elements. And if you use wall elements, I don't know, 2, 3, 4 elements should be sufficient in most cases. If you use a beam, you could embed the beam at the same level as the beam. And I put the beam at the level of the floor slab, basically, here. Or you might think it might be better to connect it in with some vertical stiff beam elements rather than using horizontal ones. And this is just an option. So these are extra elements which connect to the wall, the main beam elements, some extra elements, just to provide the connectivity. And again, the extra beam elements must not add stiffness to the wall. For example, you don't want these elements to have any axial stiffness, because if they do, they'll act like reinforcement to the wall, which may not be a good idea. So one of the things you would do would be to specify a beam that doesn't have any axial stiffness or any significant axial stiffness. On the other hand, in bending, it should be pretty stiff. A deep coupling panel, it's almost certainly controlled by shear, and a single element with shear, with a single wall element with shear should be sufficient. Now, one of the things that you will often do in linear analysis is to use a nice fine element mesh, based on the idea that for linear analysis, the finer the mesh, the more accurate result, or the more closely the result approaches an exact analysis for an elastic material. And this type of mesh is fine for elastic analysis. It's not necessarily necessary, but it's okay. Firstly, it doesn't require much thought. And SAP, for example, has got very nice meshing capabilities that will do the job for you. You don't have to worry about it. And if you're doing a linear analysis, the computer times aren't very great, so it may be overkill, but it doesn't really matter very much. Now, for inelastic analysis, this isn't such a good idea. Inelastic modeling requires a lot more thought. It's okay if you're doing elastic analysis. Yeah, there's lots of elements. We don't have to think about it. Nonlinear analysis, you'd better think about it. It's not a matter of just using more elements. And also, computer time becomes more important. A nonlinear dynamic analysis involves 1,000 or 2,000 or maybe even more time steps. And so the order of the computer time is going to be of the order of 1,000 times larger than it might be for a single static analysis. Much, much larger. So you need to start thinking about whether your mesh is overkill or not. And another point, and I think this one is maybe more important. The analysis results, and in particular, say, the stresses you would calculate from this type of thing, may be accurate for an elastic material, but reinforced concrete is not an elastic material, so it's not accurate. And it's really important to remember this. If you do an elastic analysis and calculate the stresses across this cross-section, they're not going to be anything like what you've got in reinforced concrete. The vertical stress is going to be nowhere near what you have in reinforced concrete. The shear stresses are going to be nowhere near what you have in reinforced concrete. So if you look at this in terms of, well, getting an exact analysis, you're not. It's terribly inaccurate if your concern is getting an accurate analysis. That's not your concern. Your concern is not to get an accurate analysis. Your concern is to get some forces to design the cross-sections. And the sort of thing you might do, and I want to talk to you here about true strength-based design, where you really are designing for strength, not deformation-based design. The sort of thing you might do is, if you want to design this cross-section, is take a cut through here, and from the stresses on those elements, calculate the bending moment and the axial force and the shear force, and then design that cross-section for that bending moment, that axial force, and that shear force. And that's okay. The stresses themselves are terribly inaccurate, but the axial force, moment, and shear force you calculate are plenty accurate enough for doing a reinforced concrete design. Now, your purpose wasn't to get an accurate analysis. Your purpose was to provide sufficient strength capacity in the structure, and you can do that from an elastic analysis. The shear stresses may vary in your analysis dramatically across the width, and they may be parabolic over the width. But that's not what really happens in concrete. In any case, you're just going to design you're not going to design each individual element with a different amount of shear reinforcement. You're going to have some shear reinforcement and just use the average shear stress over the cross-section. So, the stresses may not be accurate. The second point, nevertheless, for true strength-based design, reinforced concrete cross-sections designed using the analysis results are probably or almost certainly okay. The problem is if you're talking about earthquake design, these cross-sections may not be okay for earthquake design where there can be inelastic behavior. And that really is a key point. If you're using true strength-based design, an elastic analysis of this type is nowhere near accurate, but it's plenty good enough for getting force demands and force capacities, but force demands primarily. If you're doing an inelastic analysis, that is really no longer the case, that a mesh like this may actually be counterproductive. So, and I'll be talking a little bit more about this. Let's look at the modeling of 2D inelastic walls now, and just for the bending case, or actually combined axial force and bending. A key aspect is PM interaction. The axial forces can be substantial, and even if they're not, when you bend a reinforced concrete cross-section, you get a shift in the neutral axis, and so some things happen. And elastic analysis does not tell you this. So, there is another reason why elastic analysis is not terribly accurate. So the neutral axis location shifts, and it depends on the P over M ratio and the amount of cracking and yielding and a bunch of other things. This shift is not modeled in elastic analysis. What we do in Perform 3D, we don't use an interaction surface, we use fiber cross-sections, which is interaction surfaces and plasticity theory do not apply properly to reinforced concrete. It would be a big mistake, I think, to use them for walls, so we use a fiber section instead. Fiber section might look something like this. The diagram on the top shows what a section might look like. You might choose some steel fibers, in this case with 5 fibers, and you might assign stress-strain relationships to steel that look something like this. For the concrete, it might be an idea to have smaller fibers near the outside, and you can use larger fibers near the middle. And this would be compression now, and it's going to have some different behavior. You might decide to model crushing, or you might decide not to. It actually is kind of nice if the concrete doesn't crush, and it probably really shouldn't crush significantly, otherwise it could be a bad design. It's not a nice ductile behavior if your concrete crushes. The steel fibers can yield, and they may degrade under cyclic loading. The concrete fibers can crack, possibly crush. Usually you'll specify 0 tension strength. You don't have to do this in Perform. You can specify tension strength if you wish. But once it cracks on the first cycle, the tension strength is gone anyway. So it's more convenient, easier to ignore any tensile strength. And unless you expect substantial crushing, I suggest omitting this brittle strength loss and just going ahead with the assumption that it's not going to exhibit brittle strength loss. If we look at an inelastic wall element, what you would do for a pier, for a vertical axial unbending, this is where you would use the fiber section. The horizontal cross-section is a fiber cross-section, and the fibers run vertically. So when you have axial extension and bending, this deforms the fibers. Horizontally, it's assumed to be elastic. You still have axial extension and bending, but in this element, it's assumed to be elastic. And I'll talk about shear later on. That can be elastic or it can be inelastic. It depends. So the vertical axial and bending deformations affect the fibers. The others don't. And the fiber section accounts for PM interaction. We'll consider shear later. If you're using inelastic wall elements to model beams, there's a couple of things you can do. You can rotate it so as it's horizontal. And we're talking just about the bending part now. I'll talk about shear in a moment. So you can do this now. It's elastic vertically, and you've got fiber sections for horizontal deformation and bending. Or you can, in Perform, you can use a different element which has got fibers in both directions. This in Perform is called a shear wall element, and this is called a general wall element. Or if you're modeling beams, you could use beam elements. And often, I think beam elements may be better for modeling beams than than wall elements. Okay, if we're using fiber cross-sections, how many fibers do we need? And I think there's a tendency here for people to think, well, more is better. Well, more is more expensive. It's not necessarily that much better. You don't really need huge numbers of fibers. I would suggest if you've got even a pretty wide pier, that 8 to 12 steel fibers and 8 to 12 concrete fibers over the complete width would be sufficient. If you have a beam and a narrow pier, then fewer fibers would be sufficient. And if you have a deep panel which is controlled by shear, you might as well assume it's kind of elastic in bending and just let the inelastic deformation be shear. And you may need to experiment with a small model of a single pier or beam to decide on the number of fibers. It's never exactly clear how many you should use. I think this would be a reasonable guidelines. Don't use huge numbers. It's expensive and not necessarily better. Okay, key aspect for bending behavior is that when a wall element yields in bending, it behaves like a plastic zone in a beam or column. It's a constant curvature element. So a wall element which is yielding is very much like a plastic zone in a beam. And as with the plastic zone, a key parameter is what is the zone length. You've got a fiber cross-section. In effect, this means you've got a moment curvature relationship, which is defined by the properties and locations of the fibers. And if it's a plastic zone, the plastic zone length should be such that you can use the actual moment curvature relationship with, so it's good enough for practical purposes. It will never be exact. ASCE 41 is fairly specific. It specifies a hinge length of 0.5 times the pier width or the beam depth, but not greater than the story height. And this is similar to the 0.5 beam depth that we were talking about previously for plastic zones and beams. So it's essentially the same as a plastic zone, and for practical purposes, it seems to be a reasonable rule. You can't be absolutely sure about that. This seems to be pretty good. And the point I made before is the bottom one, that the plastic zone is correct if you can use the actual moment curvature relationship. Okay, what might this mean? There's some simple examples for the hinge or the plastic zone length. If you have a solid wall where a hinge forms at the base, then you would have an element which is 1/2 the width, and you might have to have some other element to take you up to the story height. If you have a coupling beam using wall elements, these might be 1/2 the depth, and these ones might just fill in the difference. And if you use a beam element, you might choose to put, and if it's governed by bending, you might choose to put the hinges at d/4 out from the column face rather than right at the column face. And it would be equivalent to using a plastic zone of 1/2 of the wall depth. The problem is that it's not so simple when you look at real walls. Here, if you have two piers with rather weak coupling beams, so not very much coupling, you might use 1/2 of W1 here and 1/2 of W2 here. But if you have strong coupling beams, it tends to act more like a single cantilever, and you might decide to have a single hinge, in which case it might be the story height. Another problem is that the hinge length that is specified may not match the elements. Now, this is not necessarily a good mesh, but it is just an example. If the hinge length was a story height, this could extend over several elements. And so this, I'm going to talk about an aspect of which is rather important, is as you refine the mesh, you don't necessarily get a better result. You may tend to get a worse result. I'll come to this in just a moment. It's convenient if the finite element mesh matches the hinge length, but it's not generally possible, and it's usually not necessary. And we're going to address this issue more when we consider performance assessment. What are the demand capacity measures, and how do we calculate them? That's going to come up more later on. So some key points and a suggested procedure. The hinge length applies only for bending, and if a member is controlled by shear, the hinge length isn't really that important. So it's only if for members where you have substantial bending. The hinge length is important for performance assessment, as I just said, and we'll look at this later on in this session. The hinge length is less important for the finite element mesh. You can have several elements within the mesh, within the hinge length if you wish. I'll give an example in a moment. So if bending in a pier is important, estimate a reasonable hinge length, and often it can be the story height. It's very nice if it can be, because that just gets around the problem. If bending in a beam is important, consider using a beam element rather than wall elements. If you use wall elements, use 1/2 the beam depth as a reasonable hinge length. And use a reasonable element mesh, consider the hinge length, but you don't have to have an element which exactly matches the hinge length. Let's look at the shear now. That was pre-bending. If we look at shear, if we look at an inelastic shear material, or maybe the behavior of a complete cross-section, it's typically fairly brittle. Experiment might show something like on the left-hand diagram, and the right-hand diagram shows something that you might use for analysis. So it tends to be brittle, and in Perform you have two choices. You can assume that the behavior in shear is elastic, and you can check the strength and make sure the strength demand capacity ratio is less than 1, or you can allow inelastic behavior and check the deformation. Elastic shear is fairly easy. Inelastic shear is a lot more complex. The wall element for shear, just the axial and bending part, we've used a fiber section here. We're talking about an inelastic shear behavior. What is done here is to specify a material with an inelastic shear stress, shear strain relationship, something like this, and then assign that to the element, and that determines its behavior in shear. Shear stress and strain are constant over the element. In a pier or a beam, the shear force is usually constant over the member length, and that's easier than the bending, where the bending moment varies linearly. So there's no need for a hinge length for shear. The shear strength, typically you will calculate the shear strength using ACI or maybe other formulas or maybe experiment. One of the complications is that the shear strength may depend on the axial stress as shown below, and for compression, the shear strength may increase, and for tension, the shear strength may decrease. And in Perform, if you assume that the material, shear should be elastic, then Perform allows you to take this effect into account. In other words, it's calculating the strength, and it can take this effect into account in calculating the strength. But if you use an inelastic shear material, Perform currently doesn't allow you to do this. Basically, you have to specify the shear strength, and it's assumed to be constant and independent of the axial force. And that's mainly because the effect tends to be like a frictional effect, and it's actually extraordinarily difficult to get it to work reliably when you have friction. Friction is very complicated. So in the present inelastic shear material in Perform, you have to take into account the axial force at the time you specify the shear strength. The Perform will not automatically vary the shear strength for you based on the axial force. Shear modulus, the usual formula for the shear modulus is shown at the top here. It's pretty common. It's about 0.4 E, with Poisson's ratio is about 0.25. This is fine for steel. That gives you for elastic behavior, gives you pretty good estimate of what the shear modulus is. But it's not okay for concrete, because this formula up on top applies for an elastic material, and reinforced concrete is not an elastic material. It cracks when you have shear, and what happens if you apply this formula is it's way too big. It gives you much too large a shear modulus. So the thing that might happen if we look at the shear stress versus shear strain relationship, what will typically happen is maybe there'll be no cracking to begin with, then cracking will occur. After cracking occurs, it softens dramatically. And the ultimate strength here is basically reached when the shear reinforcement yields. And I'm not going into the details, but you can kind of show by playing around that this is roughly about 0.004 strain, 0.4% strain. And then if you take the shear stress and you divide it by 0.004, you're going to get a much smaller, I think I made a mistake here. This is correct. The strain that you would calculate based on G is 0.4 E, which would be this strain here, is going to at the yield strength and shear is going to be much smaller than this. It's a tenth or even less of this. I didn't do a very good job there. The important thing here is that a shear stress based on simple formula is not very accurate. This is a little more detail here. Before cracking, it's actually okay to assume G is 0.4 E. After that, it's much less. If you were going to use either a linear behavior for shear or an elastic perfectly plastic behavior, you really should use an elastic modulus which is substantially smaller than is given by this formula. And it may be of the order of a tenth as large. In many cases, the amount of shear deformation doesn't matter very much, and if you're off by a factor of 10, it may not have a huge difference. But as you get into walls, shearing deformations do tend to be more significant part of the total deformation, and if you're off by a factor of 10 on the shearing deformations, that could be a serious error. So you do have to be careful here. Let's move on now and look at three-dimensional walls. Here we get into the shear lag effect. And what we're looking at here is a couple of three-dimensional walls, T-section walls. And these are both elastic. And if the wall is short, you get substantial shear lag effect as the vertical stress out here at the edge of the flange is substantially smaller than it is where it connects to the web. As you get taller, this becomes more uniform. You get little or no shear lag. And these are the bending stresses at the base, assuming elastic behavior. And one of the questions that arises, what is the effective width? Now, what this is that if you do an elastic analysis, it's theoretically the longitudinal stress kind of tails off like this because of shear lag effect. This might be a theoretical distribution, something like this. An effective width is something which has got the same stress as the maximum here and has got the same area. And if you choose a flange with that effective width and ignore shear lag effects, you're going to get pretty much the same effect as if you choose the true width and you did account for shear lag effects. So you must, but when you do this, if it's inelastic, it becomes a little more complicated to figure out what is the effect of shear lag. Firstly, you must account for inelastic behavior, and you must account for cyclic loading. And in the next 4 points, I've indicated what suggestions have been made for the effective width. Now, the first one here is from Powell and Priestley's book. They suggest for strength that the effective width as a multiple of the height of the wall should be 0.5 for a flange in tension, 0.15 for a flange in compression. There's something counterintuitive here that when it cracks in tension, you would expect the shear modulus to be smaller, and therefore you would expect the amount of shear lag to be larger, so you'd expect the effective width to be smaller. But it's nonlinear behavior is not what happens, and one of the things that Powell and Priestley observe is that in compression, after a few cycles, there's only a small amount of concrete which is in compression, and most of the other is still cracked, even when it's in compression, which is why they have a smaller value here. Whereas in tension, it can tend to bring in quite a lot of the tensile reinforcements, and it's probably probably not a bad idea from a strength-based design to maybe overestimate this a little bit so as you also overestimate the concrete stresses. Anyway, 0.5 for flange and tension, 0.15 in compression. And this is for calculation of strength, not for calculation of stiffness. ACI 318, 0.25 for strength. And that's based on a flange and tension, and this compares with Powell and Priestley recommendation of 0.5. FEMA 273, 0.1 for strength and 0.2 for stiffness. And there's kind of sort of a typographical error in ASC 41, which means it's unclear. But the point I want to make here is here we've got 0.1, 0.25, and 0.5 from 3 different sources. And so you throw up your hands in the horror and say, what on earth am I supposed to do? Well, I'm not really sure, except in most cases it's not going to matter, as I'll show in a moment. But this is, it could be a serious issue. The effective width depends on a lot of things. The shear modulus, whether the flange is in tension or compression, the amount of cracking and concrete crack and steel yield, how many cycles you've had whether there is biaxial load on the wall, or there could be load acting in this direction and in the other direction, and that's going to affect things. And if you're running analysis, it can also depend on the finite element mesh. If you use a finer mesh, typically you'll tend to get a larger shear lag effect than if you use a coarser mesh. So what do we do? If it's a slender building, just assume the full section is effective. The height will probably be sufficient. In almost all tall buildings, you don't have to worry, which is nice. If you have a squat building, you could model it as a three-dimensional structure and hope that the modeling would take a kind of shear lag effect. Or you could split it into two separate walls, and you could put a flange on the end of each wall to account for the flange effect. I don't like the second method very much. If it were me, I'd be inclined to just go ahead and use the three-dimensional one, but I have to admit I really don't know, and this is a tricky problem. This is something which really needs some research. Another complication is the effect of the floor slab on the beams, and this just indicates if you have a beam here, the cross-section might look something like this, where a substantial portion of the floor slab might be effective, and if it's behind an elevated door, then the slab might be on top, and you might have an L section. So if there is composite action between the slab and the beam, it must be considered when you model the coupling beams. This can obviously be pretty important. Piers are not affected very much here. And it's common in analysis to assume that floors are rigid diaphragms. And remember, rigid does mean rigid in a rigid diaphragm. And so you're basically assuming that this is a rigid slab, which means your neutral axis is going to be at the slab level, because there the strain will be zero. That's an issue you need to consider. The seminar notes do include some modeling suggestions. Deformable floor diaphragms. Now, this is a plan view, and basically this would be a shear core, and then there's some walls around the outside. And you might want to consider deformations in the floor diaphragm. And as with linear analysis, it's common in linear analysis just say, well, let's just assume a fine mesh and let everything take care of itself, which is fine for linear analysis, but for nonlinear analysis, that's not so fine. You've got to be more thoughtful about this, because this can add tremendously to the computational cost if you start using these fine element meshes. You've got to ask yourself, what is happening? What's really going on? How does the wall work? And try to get away with using far fewer elements. Maybe even use bar elements, use like a truss model rather than a wall model. And I can't really offer too many suggestions on this, otherwise you take a look at what is really going on in the structure, then ask yourself how you can reasonably model it from a practical point of view. So let's move on now and look at demand capacity calculation. And firstly, for axial bending, which we'll assume is inelastic, so we're talking here not about strength but deformation. The performance considerations. The main considerations for the Pearson beams are the axial bending behavior and the shear behavior. Axial bending behavior usually involves steel yielding, concrete cracking, and possibly concrete crushing, although preferably not. So it will be inelastic. The inelastic axial bending behavior in the piers may be limited to a hinge region, which is usually at the base, using capacity design. I think if you follow Tom Paule's procedure for designing shear walls, you would say, okay, we're going to allow a hinge to form at the base. We'll design the rest of the structure to remain essentially elastic. It can crack, but you wouldn't want to get any significant steel yield. You would also design the upper stories to not to yield and shear. And in the hinge region, you would be very careful to design for shear strength, also recognizing that the larger the hinge rotation, the weaker it is in shear, so you've got to add more shear reinforcement at the base than you otherwise might. And that's what indicates here. Now, moving down to the second to last point, the shear in the coupling beams and panels may be inelastic. In fact, a coupling beam could be regarded as a sacrificial component which would allow larger inelastic deformations. A coupling beam is not essential to stability of the structure. If a coupling beam failed completely, so as you had some individual uncoupled walls, the structure might still be okay. So you don't necessarily have to treat coupling beams as primary components. You could consider them as secondary components. And if you do this in ASC 41, if a member is a primary component, generally speaking, the deformation capacity has to be no larger than the ductile limit. But if you treat it as a secondary component, you can allow deformation capacities which are larger than ductile limit. It means it can lose strength and undergo substantially larger deformations. This is a design decision you have to make of whether you would regard these things as sacrificial or not. In ASCE 41, the demand capacity measure for a wall in axial bending is rotation over this hinge length. Remember, the hinge length is 1/2 the wall width or the story height, whichever is smaller. And the demand capacity measures rotation. It's kind of like rotation over a plastic zone length, which is not too different from rotation on a plastic hinge. So in ASC 41, the deformation demand capacity measure is rotation, similar to the rotation in the hinge or plastic zone. And ASC gives capacities in terms of the plastic rotation after yield. Elastic rotation might be small. A couple of things can happen. This is a T-section wall. So when you bend it in one direction, the neutral axis will shift a lot. When you bend it in the other direction, the neutral axis will not shift as much. The effect is going to be the concrete is more likely to crush in the second case. It's like an over-reinforced beam. And an over-reinforced beam is more likely to crush, so it'll be less ductile. This one here is an under-reinforced beam with lots of compression strength. So the rotation capacity for A in ASC 41 is larger than the rotation capacity for B. I haven't shown this, but large axial compression force will also reduce the capacity. And in the hinge region, there are two things happen. I've already said that in the hinge region, the shear strength is affected by the hinge rotation. But there's another aspect of that, is that the larger the shear force, the smaller the hinge rotation capacity. The shear force also affects the rotation capacity. You start getting some of these nasty interactions. Here's some ASC 41 rotation capacities. And if it's under-reinforced, which is case A, and let's look at the collapse prevention, you'll add 1.5% rotation. If it's over-reinforced, like case B, 0.9% rotation, substantially smaller. An alternative measure is strain. And we get now into strain calculation, and when you calculate strain, you have to talk about strain over a particular gauge length. And in this particular case, the gauge length for calculating strain would be exactly the same as the hinge length. Usually for taller building, it's the story height. It's a reasonable gauge length for calculating strain. And if you look at this, the rotation is theta, and the fiber strain is just theta times d divided by L. That's pretty straightforward. So it's not difficult to convert from rotation to strain. If we look at what might happen for a particular case of the capacity I just indicated before, let's assume that the hinge length is 1/2 W, so L is 1/2 W, and let's consider strain on the extreme tension fiber. And if we look at the under-reinforced case, then the collapse prevention rotation capacity from ASC 41 was 1.5%. If I assume an effective depth of 0.85 W, this translates into a strain of 2.6% in the steel. If you do it for bending the other direction, consider the other extreme fiber, the rotation capacity we just had before was 0.9%. If you assume the neutral axis is about the middle of the cross-section in this case, then this translates into about 0.9% strain. So the difference between the two rotations is not that large. The difference between the two strain capacities is quite substantial, almost a factor of 3 to 1, and that's sort of pretty much what you might expect. Now the problem that comes in is the hinge length may not exactly match the element mesh. In Perform 3D, you can, if you wish, calculate rotation or strain in individual elements. So, for example, I could calculate the rotational strain in this element and use that as the demand rotation or demand strain. But that's not the same as the hinge length. That's a different gauge length from the story height, which would seem a reasonable value. And let's take a look at what is going to happen. One of the problems is that as you subdivide the mesh, as you make the mesh smaller and smaller, and the strains that you calculate will tend to get larger and larger. And if you go far enough, it doesn't matter how fine you make the mesh, you go finer and finer, the strain keep getting bigger and bigger. The strain in an individual element, the gauge length gets shorter and shorter, the inelastic deformations get more and more concentrated, and the strain you calculate in like this worst element just keeps going up and up. Refining the mesh doesn't help you get a more accurate result if it's inelastic. However, what we really want to do is calculate the strain over this gauge length, which is this hinge length. And what this next one does is say, okay, suppose that we take, in this case, a simple cantilever and just do both pushover and also a dynamic earthquake load. I'll show the results in just a moment. And let's look at a single element over the hinge length, 2 elements over the hinge length, and 3 elements over the hinge length. So the hinge length is the story height, 1, 2, and 3 elements. And then calculate 2 strains, the strain in the lowest element and the strain over the story height using, well, it's a strain gauge element in Perform. I'll show this in a little more detail later. You can paste a strain gauge element on top of this thing and it'll calculate rotation for you and strain. And also, let's calculate rotation over the story height. And this is done in Perform using a rotation gauge. I'll discuss these gauges in just a moment. And so let's compare the calculated strains and rotation in the 3 cases. Firstly, if we look at the strain in the worst element, what happens? Secondly, if we look at the strain measured over the story height, what happens? This is, first one is static pushover, and it's pushed in each case to a 2.3% drift. The strain in the bottom element with 1 element is 2.4%, 3.7%, 4.2%. As the elements get smaller, the calculated strains get larger. Not good. If you look at the strain over the story height, though, it's pretty stable. In fact, it's remarkably stable. I'm not sure this will be really this close in practice, but it doesn't vary that much. Similarly, if you look at rotation over the story height, that doesn't vary very much. So as long as you measure the strain or the rotation over the proper gauge length or a consistent gauge length, then it doesn't really matter very much if you use a finer mesh. It's not that sensitive to the mesh. But if you calculate the strain or the rotation in the worst element, it can be very dependent on the mesh, which is not good news. So you should use rotational strain over the hinge length. And as I'll indicate in a moment, the way in which you do this is to use a strain gauge or a rotation gauge element. This is a dynamic case, and this case actually worked remarkably well, but these are, again, 3 different elements, and this is a dynamic earthquake, and the roof drift was pretty much the same in each case. It wasn't very sensitive to the finite element mesh. The strain in the bottom element, again, increased substantially from as you made the mesh finer, but the strain over the story height did not change that much, and the rotation over the story height did not change that much. And there's an interesting point here that for the same drift, you got rather different strains for dynamic analysis than you did for static pushover analysis. In Perform, these rotation and strain gauges are exactly like that. They're just exactly like a physical strain gauge. One of the things they do is they don't affect the bandwidth of the structure stiffness matrix. They're just there to measure strain, so it doesn't matter. You can stretch them from top to bottom of the structure if you like. It'll have no effect on the behavior. So this is a better way of doing it than calculating strain in individual members. The procedure, therefore, use strain and/or rotation as the demand capacity measure. You choose a reasonable gauge length, which is usually the hinge length. This is the gauge length for the strain gauges, and it will often be the story height. And then you use strain and/or rotation gauges as you need. Let's not worry about the remainder. Next topic is shear strength. And we're talking now about assuming that you're going to design for the structure to remain elastic in shear, not inelastic. You can calculate the shear strength using the ACI code or other sources. what you would do in Perform is you assign the strength to a shear material, and then you would assign this material to an element. So if you were doing a shear strength calculation at the element level, you would take a typical element. It's got a shear force, it's got some axial force. You've assigned a shear material to this element, and so it will, at each step in the analysis, it will calculate V and P, and it helps it calculate the demand-capacity ratio for shear strength. You can do this if you wish. The problem is you run into the same problem that you had previously, is as you refine the mesh, you may start getting larger and larger shear strains. Not as much as bending, but there does tend to be some shear strain concentration. If you look at the shear strains in these three elements, they're likely to be substantially different. And basing the decision on the worst of these three elements might not be such a good idea. In practice, you'd want to consider the shear strength of the complete cross-section. That would be more practical. And Perform allows you to do that. So usually it's better to check the shear strength for a cross-section which covers several elements, and this is because there may be shear stress concentrations. What you can in Perform is you can assign a shear strength to a cross-section. It's shown here. You can cut a cross-section and assign a shear strength to it. And then during the analysis, Perform will calculate the axial force and the shear force on that cross-section, and we'll do the strength calculation. And again, let me emphasize, we're talking here about the assumption that it remains essentially elastic in shear, so this is a strength check. And generally speaking, it's a better idea to check the shear strength on a cross-section than it is to check it on individual elements. There are some, we've shown these diagrams before. The axial force and hinge rotation can both affect the shear strength. And, well, Perform currently doesn't do this. It does for frame elements, but currently for wall elements, it will account for the effective axial force on shear strength. But if you're talking about the shear in the hinge region, there is no provision in Perform to account for the hinge rotation effect on shear strength in a wall element. You can do that in a beam or a column element, but in a wall element, for shear in the hinge region, you must estimate you must take into account the amount of expected hinge rotation at the time when you specify the shear strength capacity. Perform will not account for the hinge rotation for you automatically. Moving on now to shear deformation. The shear deformation measure is what in ASC 41 is called shear rotation, which is really just shear strain. So the deformation measure is shear strain. Typical ASC 41 capacity for a pier is about 0.75% for the collapse prevention level. For a coupling beam, if it's conventional reinforcement, about 1.6%, diagonal reinforcement, about 3%. This is sort of order of magnitude of shear deformations that are permitted. And it's not a good idea to look at the shear strain in individual elements, because just as there may be shear stress concentrations, there can be shear strain concentrations. It's better to use a shear strain gauge, and what you can do is you can plaster a shear strain gauge. You could plaster it over a beam, over a complete story, or over some portion, and then use the shear strain in that gauge as a demand capacity measure rather than in individual elements. So other aspects, P-delta effects. You can consider P-delta effects in walls and Perform just as in beams and columns. When you have wall elements, you just say whether or not you want P-delta effects to be included. Or alternatively, you could use a separate P-delta column. If you're not familiar with this, don't worry, it's just another way of accounting for P-delta effects. And I do always recommend that if you're running an analysis with P-delta effects, then turn the P-delta effects off first, run your model, make sure it's working okay, and then after you're sure it's working okay, turn on the P-delta effects. Because I've seen often people just do everything. The first analysis people will run will be a dynamic analysis with strength loss and P-delta effects, and then they'll wonder why it didn't run the first time. Start off without any P-delta effects, run a static analysis, and also suppress the strength loss also. And Perform allows you to do this rather easily. You can turn on and off P-delta effects easily, and you can also suppress the strength loss temporarily if you want to with very little effort. just build up the model carefully, because it's not going to work if you just try to put everything in, including the kitchen sink, and hope it's going to run first time. It's not going to happen. And then finding out what's wrong is really going to be an issue. Out-of-plane behavior. Now, out-of-plane behavior is plate bending. And Perform assumes that this is elastic, and so it will not do a cracked slab analysis. We do have another program, Perform Collapse, which does have a cracked slab analysis, but this is not available in Perform 3D. So out-of-plane bending is elastic, and it's also separate or uncoupled from the in-plane behavior. And let's not worry about the rest of this. It's kind of a detail. The support conditions at the base. What I've seen is that what people mostly do, in the case I've seen, is use hinge supports at the base. And that implies for out-of-plane bending, which would imply that along the base for out-of-plane bending, you've got a piano hinge type of behavior. I don't think you would really have that in practice. I think for out-of-plane bending, it's much more likely you've got a footing or something, and it's going to be closer to fixed. And what I would like you to do if you're running this is run fixed supports. And there's a couple of reasons for that. Firstly, there's a bit of a problem with the Perform 3D wall element, and if you do assume hinge support, sometimes it can give you trouble. But secondly, it's probably more realistic. Concrete crushing. Here we have a wall section, and here's a couple of possible sets of concrete fibers, one with some pretty big fibers and one with some much smaller fibers. This is rather a complicated issue. In an actual section, cracking and crushing will spread continuously across the section, so that the neutral axis sort of moves continuously. But in a fiber section, it goes discontinuously. As each fiber changes state, something happens, and the neutral axis jumps from point to point. If there's no crushing, it's probably sort of okay to assume things like this, and the neutral axis could move this far, and then it wouldn't go any further. It would jump from this point to this point. If there's crushing, maybe you need more elements, and this is a tricky one. Now, I would hope that you would not get very much crushing in a wall. It's not a reliable way of dissipating energy. If you do expect crushing, then you probably should use smaller elements towards the boundaries of the wall, and you probably should include strength loss in the concrete stress-strain relationship. If you don't expect crushing, you can use larger fibers, and you don't have to worry about strength loss in the concrete. Diagonally reinforced coupling panels. If you wish, you can model these using steel strut and steel tie and concrete strut elements. It's possible, and just to indicate roughly how you might do that. Each of these would be a concrete strut which resists compression and a steel tie in parallel, and the same here. So when a diagonal extends, the concrete cracks and you just have steel. When the diagonal is in compression, the concrete strut is in compression, so it's much stiffer. So you could use this type of model if you want. Irregular meshes. SAP is really good at allowing you to change meshes. You go from place to place, for example, from a coarse mesh to a finer one. We don't have this capability yet in Perform. You really basically can't change the mesh like that. You probably don't really want to very much, but there may be some cases, and that's something we're working on. Currently, we don't allow it. Distorted elements. If you had some irregular holes, you could use a mesh like this on the left, but it would also be okay to use a mesh like this on the right. The elements don't have to be rectangular. They just shouldn't be badly distorted. If you have a wall supported on columns, there's a couple of ways in which you could do it. You could model these columns using wall elements. I've shown here 4 elements. Or you could use column elements, frame-type elements, in which case you'd have to have some embedment in there. This can be a tricky one to model. What I recommend when this issue comes up is we'll take a look at what's actually happening in the real structure. And it can vary depending on the nature of the structure. But based on what is happening in the real structure, come up with a model you feel captures that behavior fairly accurately. And in some cases, it might be more appropriate to use wall elements. In other cases, it might be more appropriate to use column elements. This is another of the issues where it's very difficult to get it exact. You just have to get it good enough. Foundation flexibility can have a significant effect, and I think many of you are aware of this. It's nice and easy to assume a rigid foundation for a shear wall, but shear walls crank lots of bending moment into the foundation. They may well deform them, and you may have to account for foundation flexibility. One approach is to estimate the stiffness and model it using support spring elements, but if it's more complicated, you might have to model the foundation explicitly, and somebody asked a question about this earlier. And if you do have to model explicitly, that's more of a problem. It's your decision of how to take this into account. Bending moment envelopes is another issue. I'm going to show an example of this in just a moment, but when a wall hinges at the base, the maximum bending moments, the moment envelopes that you get, can be quite different from the case where the wall remains elastic. It has to do, I think, with the higher mode effects and the fact that when a hinge forms at the base, the higher modes kind of change shape. I'm not sure exactly what's happening. But an elastic analysis can give you an incorrect picture of the behavior. And this sort of illustrates this. Now, elastic analysis and inelastic analysis would not give the same bending moments at the base, but just suppose you normalize them to be the same at the base for this purpose. The moment envelope for elastic behavior for a wall like this is likely to be roughly straight, including higher mode effects. But the moment envelope you would get from inelastic behavior is more likely to be like this, and in particular that means it's more likely to give you higher bending moments higher up in the structure than you would anticipate from an elastic analysis. In other words, if you design the upper part of the structure using the forces moments from an elastic analysis, it may be under-designed. It may hinge up there. The same is true of shear. The shear can be quite different. I'll show this in an example in just a moment. So let's take a look at a couple of examples here. This is a shear core, which it's basically a channel wall here. These are coupling beams, and then an I-section wall here, and these are coupling beams. So if you look at it looks like this in one direction, where these are all the coupling beams, and in the other direction, it's a solid wall. This wall was designed, my understanding, using code design procedures. And there is a study going on as ATC 63, which is looking at a number of things. And this is one of the structures they're looking at. And I was kind of interested, so I modeled the structure to see what would happen. And I just want to look at the finite element mesh, and then something about the behavior, which may or may not be typical of buildings designed by code methods. I'm not really sure, but it certainly happens in this one. What I've done here is use two elements in the base, and one of the reasons is to use small elements here just because this is not a very wide wall, and so I just wanted to get a smaller element, and then those same elements go around the corner. Higher up, I've used just a single element per story. So in the bottom floor, two elements over the height, upper floor is one element. Across each of the three webs, I think it's adequate to use a single element across the width. This is a 12-story building. That's a pretty slender beam. Plane sections remain plane. There's no reason to use several elements across the width. It's unnecessary. It's overkill. And also for the flanges, it's okay to use one element across the flange width here and one element across the flange width here and here. You don't need a fine mesh to do this. It is done using fiber sections, and to save time, I'm not going to go over that in much detail. There are a number of different ways in which you can do it, but I think it's better to take a look at the Perform user guide, and then also when you get to Perform 3D, you currently get a frame example, which is sort of a walkthrough example, and there's some documentation which walks you through the frame example so you get a feeling for the structure. We don't have a wall example yet, and what I plan to do is to take this example and make it into a walkthrough example so as you can take a look at it. And I don't think there's much point in going into a lot of detail right now, but ultimately we'll have that and you can sort of go through and see what I think would be reasonable means of modeling this. The way it has been set up is it uses fiber sections over the whole height. And the reinforcement varies over the height for axial bending effects based on the moment envelopes that were calculated from a linear analysis. And then the shear strength actually in my model is constant over the height, but that's kind of a detail. And I've got some rotation gauges, and there they are for, basically I've just plastered a rotation gauge over each of the, and you may not see this very well, but at the base here, there are two actual elements, but a single rotation gauge. It's the same kind of thing I was talking about before, is the rotation is being measured over the story height, not over individual elements. And let's look at, I've run a number of analyses, or let's also look at the coupling beams. Okay, the coupling beams are allowed to yield in shear, and I've set up this is the shear force versus shear displacement relationship for one of the coupling beams. That varies over the height of the structure. It actually varies. There are 4 different cross-section properties, but this corresponds actually to a diagonally reinforced coupling beam, and this would be pretty much what what ASC 41 would specify. There is a brittle limit here, but it's not a great deal of strength loss. And if you look at the deformation capacities, I've only done it for 2. The first one here, this is treating it as the collapse prevention level and as a primary component, which means that the deformation cannot exceed the ductile limit. And second one, which is as a secondary component, where ASC 41 gives you a larger capacity, which exceeds the ductile limit. And one of them happens to be 2.2 inches deformation, shear distortion, shear displacement across the hinge. The other 3.6 inches. The details don't matter very much. And if we look at it's an in view, and we're going to do an earthquake. Okay. This thumbnail is what is happening with the earthquake, and I'm going to just set up all of the deformation limit states. It's doing rather a lot of calculation here. But at the end, let me actually do a little bit more here so as we can make this one show up a little bit more. It's really quite strong. So I'll make that 0.1, 0.2. 0.3 and 0.4. Okay, now what you observe here is that down the base, these now are going to be rotation demand capacity limits, is that it's in the yellow, which means it's between 0.3 and 0.4. Up here at the 6th story, it's in the red, which means it's larger than 0.4. And to cut a long story short, this structure looks as though it does not going to yield at the base, it's going to yield at the upper story. And my analysis shows this, and then the ATC 63 project has done also analyses using similar models, and they find the same thing. So if this was designed using conventional code-based design procedures, Nonlinear analysis would suggest it may not be a very good design. The other thing can happen is that if we look at shear strength, and what I need to do here is to what do I do? My own program, and I can't figure out how to use it. Here we go. What I've done here is defined a series of sections at the base, first story, second story, etc., all the way up. And I have assigned strength, shear strengths to those cross sections. And they're through the complete wall. So 3 webs and everything. And I've assigned strength to them, and it can plot the strength demand capacity ratio. Okay? And I can plot that. And this is the envelope, and this is what it looks like. And here's 1.0. And what this one says is the strength demand capacity ratio reaches a maximum of 1.7. The suggestion here, the indication here is that this structure does not have sufficient shear strength, and it is likely to fail in shear at the base. And again, the ATC 63 people found a similar result. They ran a whole series of earthquakes, and they found that in a number of cases, the failure was hinging at the 6th floor. In a number of other cases, it was shear at the base. In a very few cases, only a very few cases, it was hinging at the base. Now, I can't say that this is a result that is a general result, but it kind of indicates in this particular case that perhaps a conventional code design may not give you a structure with very good performance. Let me do one more brief example here, and this just to illustrate a point. This is it's a 10-story wall. It doesn't need to have 2 elements across the width, but I got the model from somebody else, and they chose to put 2 elements across the width. This actually, I just took it. It's a model of a 7-story wall that they tested at UC San Diego, and I just stretched it out to 10 stories just to illustrate a point. And the point is this: I've run an analysis with a strong earthquake, which causes the hinging at the base. And then I've run analysis with a weak earthquake, which doesn't cause any significant nonlinear behavior. So the sort of moment envelopes you get from the weak earthquake would be the sort of thing that you would design for if you were using linear analysis to do your design. What you get from the strong earthquake is what nonlinear analysis says would be present in the structure. Now, I can't compare the numerical values because one is a weak earthquake and one is a strong earthquake, but I can compare the shapes, just the same kind of thing that I did in the previous slide. And so what I have a look is at the moment envelopes for the weak earthquake, which is the sort of envelope you design for, just the shape, and then the moment envelope for the strong earthquake, which is what you would get from the inelastic case. So H1 force, and I need okay. Okay, now this is this is the shear force envelope. It's a little bit big up in here, and it's a little unusual shape, and that is for the strong earthquake. Now, let me do it for the weak earthquake. Again, this is shear force. It's pretty much a straight line. The 2 shapes are quite different. Going back again to the nonlinear case, it's not a straight line. Relatively, it's showing much higher shear forces up here at the top of the building. So here's a case where the shear forces that you calculate from a linear analysis are quite different from the shear force distribution that you would get when you do a nonlinear analysis. And if we look at the bending moment, and again, if we look at the weak earthquake first, this is the moment envelope you would get from a linear analysis. And just look at the general shape, and then the moment envelope you get from a stronger earthquake. very different shape. Much larger moments higher up in the structure rather than the linear variation. So once again, the indication is, and this has been observed by a number of people. Professor Krawwinkler has observed this many times in recent years, that when you do a nonlinear analysis on a shear wall structure, some strange things happen, and the shape of the moment envelope that you get is quite different in a nonlinear analysis than it would be from a linear analysis. Which the conclusion is, if you do a conventional code-based design where you use linear analysis, you're likely to under-design the upper portions of the structure in bending and also quite likely in shear. Okay, so moving on now with the PowerPoint. This reaches the end of this session. All we've talked about here is models and performance assessment for shear walls. They're quite different from frames. As I think I said earlier, that this one of the walls you just looked at was the first real wall I tried to model, and it does make me realize this is really not a simple task. It's actually quite a difficult task, and it does require a lot of thought. The next session is going to consider nonlinear static and dynamic analysis. Next session is for the young people who are still awake at the end of this long day. And it just gets into a lot of details about how things are done. But one of the specific things that we will talk about in the next session is damping. Damping in nonlinear analysis is a tricky topic, and I can give you some ideas of what you might do in the case of damping. Questions?
Beams, would you mind showing how you had modeled the coupling beams in the model which you had there?
Even though the bottom coupling beam was a quite deep coupling panel, and even the upper beams were actually relatively small span to depth ratio. I think they're 72 inches long and about 40 inches deep. They're still pretty deep. But I still chose to use beams, not walls. Okay, here's the bottom coupling beam, and what it consists of is a 18-inch wide by 82-inch deep elastic beam section, and then a shear hinge, which is based on the strength, and this is what I assume for that hinge. It's got a strength of around about 1,600 kips. That can't be right. 150. Yeah, it's a pretty solid beam. And so this is a shear hinge, and these are displacements 2 inches, 4 inches, and 6 inches. So it's over a 72-inch length. This is 2.16 inches of deformation. I'm not sure what that translates to into its strain, but it's 2.16 divided by 72. If you can do some calculations, that would give you what the shear strain capacity is. And I think it's 0.03, which is what is allowed by ASE 41 for a diagonally reinforced coupling beam. So it would be a 0.03, a 3% strain, or a 2.16-inch shear deformation over a 72-inch length. And it was a simple one. It consists of a length of elastic beam, a shear hinge, and a length of elastic beam. And the other ones were all the same, except they had different strengths. And then the other difference was that for the upper beams, I used horizontal embedded beams. For the lower beam, I used, this is a pretty deep beam, I used a vertical beam to connect the coupling beam into the wall. But in all cases, I chose to use beams rather than wall elements. And I'm inclined to think, in general, that's something I'd be inclined to do. You get sort of better control over the behavior if you use beam components for coupling beams rather than use wall components. Does that answer your question?
It does, and but you did not use the FEMA beams in there?
I beg your pardon?
You would not suggest using FEMA beams?
No, not FEMA beams, shear hinges. Yeah,
Shear
they're all quite deep. You know, the more shallow is 72 inches long and 40 inches deep. So it's a 1.5 to 1 aspect ratio.
Sure.
Or a bit more than that, 1.75. And they're diagonally reinforced.
But for longer beams, would it be advisable to use FEMA beams then?
If you had you have to make the decision whether it's governed by bending or by shear.
Right.
Yeah, and I think if it's governed by bending, put in moment hinges or use FEMA beams. If it's governed by shear, put in shear hinges. If you're not sure, and you should be sure, use both. Yeah.
And to add to that, is it possible for us to download this example from this?
Right now, no, but a little later on, we'll make it available. Yeah.
Okay. Thank you.
I just wanted to mention that we have done some analysis of shear walls that were designed according to Canadian codes, and we have run nonlinear analysis and observed exactly the same phenomenon, so that we have formation of plastic hinges higher up in the structure. Okay. But what was particular for our analysis was the fact that we were using like an North American records, which are very rich in high frequencies. So just by curiosity, I was wondering what kind of records are they typical of West?
You know, I don't know. I just picked one. The ATC 63 project ran a whole slew of different records, and they on their model they didn't use Perform. They used Open Seas, but they found they observed the same thing. You know, they did a statistics, and very few failed by hinging at the base. There was, I think it was roughly 50-50 shear at the base or hinging higher up. You know, and say Professor Krauwinkler pointed this out, I think, quite some time back, that you do get this effect. And it's one of the things that sometimes linear analysis can give you a wrong result. You know, and it's it's much more difficult to do nonlinear analysis, and I think there's kind of tendency, oh my God, it's too hard. Let's just use linear analysis and not worry about it. But that's not okay. You know, Pandora's box has been opened on this one. I think it's clear that there are many situations where linear analysis, even using capacity design, as they do in New Zealand, can give you a wrong result. You know, you have to.
The effective shear in the New Zealand code for 20 years has been amplified above the elastic by a factor of over 2.
No, 2.
So, well, it depends on the height of the wall. So there's another factor that comes in to account for this, what you've been talking about, but it has been in the code for quite a long time.
Oh, okay.
From the nonlinear work that Tom Paulet did with Athol Carr.
So they observed the same thing and they corrected for it. Yeah, this is a saying before. You don't have to use nonlinear analysis to use capacity design. You can do it with judgment and linear analysis. And in New Zealand, they've been doing it for a long time and doing it very well. I think over here, a lot of us don't do it over here.
Just to follow up on the 2 points. One is my original question to you on capacity design in the first session, I think, today, because I was trying to just work out whether people in the US did something slightly different from what we do in New Zealand, and I guess you don't. But on the code is based on an elastic analysis, as the codes are here, but the rules have been empirical, based on nonlinear analyses that have been done in universities and research institutes.
Professor Powell, to your left. Just to clarify, the force diagrams that you were showing, were they plotted in the direction of the coupled wall or the uncoupled wall?
Oh, they were in the solid direction. Yeah,
the uncoupled, the short way.
I could have shown you some in the other direction, actually. What happens in the other direction is that the coupling beams get clobbered and nothing else much happens. Yeah.
So speaking of the coupling beams getting clobbered, question is, if the coupling beams are located over means of egress, is it appropriate to consider them secondary or sacrificial elements?
Yeah, I don't know that's a design decision. And since I'm not a designer, I'm sure a designer has that option of considering them to be non-primary elements. Can anybody else answer that question? Do you want to design coupling beams as primary elements or secondary?
I actually believe in ASC 41, if one is performing a full nonlinear static procedure, that's a full versus the simplified, full being where you model the strength degradation, that one can use the secondary component acceptance criteria for all of your components. So that means a primary element, a conventional wisdom, the element that's there to arrest lateral displacements, it can actually go past the shoulder and experience significant degradation. So the answer is the coupling beam can degrade.
You showed us an example where you did just one element at the base, 2 elements at the base, 3 elements at the base. Do moments and shear forces also behave the same way as you showed for example, roof drift or strains?
Yeah, one of the slides that I used, which is in the book, where I took a simple cantilever wall and used 3 different 1, 2, and 3 elements in the bottom story. That was a very limited study, and all I looked at for the purpose of this was the information I showed on the slide. I could go back and look at it. I don't have it on this computer, I'm afraid. I could go back and look at it. Yeah, there are, because the bending moment is at the middle of the element. So if you have 1 element, it's looking at the bending moment halfway up the first story. When you have 3 elements, it's looking at 1/6 of the way up the first story. So those moments are sort of significantly different. And one of the things which surprised me a little is even the dynamic analysis, given that sort of difference, it didn't change things around a great deal. Now, I suspect if you ran a more complicated case that it wouldn't be quite as nice as the example that I showed. But that's the way in which you should do it. And it's not a good idea to use a fine mesh and then use a strain in the worst element. That's way too conservative.